Phenomena abound. There are so many phenomena out there that we can use to enhance the start of our lesson. In this particular video, I'm going to highlight what happened recently in New York City when it comes to electrical bike batteries and their explosion. If you, however, wish to skip immediately to the lesson that I have on electrochemical cells, voltaic galvanic cells, as well as electrolytic cells, including the Hoffman Apparatus, check the video links in the description below, in particular the timestamps. But if you wish to see how I'm going to introduce the redox unit, stay tuned. Lots of people bike in the Netherlands, whether it's in the city or in the beautiful nature surroundings. Even in upstate New York, and of course many other places in the world, you can actually bike. Where I live, the roads are extremely hilly, and so at times I've actually considered maybe I want to purchase one of these electric bikes. Electric bikes obviously means that they require a set of batteries, and there are charging stations out there that help to recharge those batteries. In New York City recently, an accident happened that involved several deaths due to the explosion of these electric bike batteries. Lithium-based batteries are not just present in bikes, they can also be in our laptops, our cameras, our phones. Lithium is even present in the batteries of certain electric vehicles, including this Tesla. Lithium batteries obviously contain lithium. There are also other metals included, but let's focus on that third periodic table element. With its 4 neutrons and 3 protons, and thus 3 electrons, it is readily wanting to lose that one outer shell valence electron. Explosive. Why are these lithium batteries so explosive? It has to do with thermal runaway, which is a chain reaction within a battery cell that can be very difficult to stop once it has started. In this animation, you can see how the temperature inside a battery reaches a point that causes a chemical reaction to occur, and it produces more and more heat, obviously very exothermic, which drives the temperature even higher, causing further chemical reactions that create more heat. Until a thermal runaway has reached, the energy stored in the battery is released very suddenly, reaching temperatures upwards of 750 degrees Fahrenheit, which is about 400 degrees Celsius. These temps can cause gassing of the battery and a fire that is so hot it can be nearly impossible to extinguish. When it comes to these batteries, these lithium-based batteries, what can we do to reduce the chance of such rare explosions? Only use authorized batteries. To avoid overheating, don't overcharge. Keep the batteries at room temp and away from any heat source. Don't store these batteries in your car or in direct sunlight, and there are qualified professionals out there that can maintain these batteries, particularly when it comes to your car. Now that we've completed the anchor phenomenon relating to how dangerous batteries can be, although this is rare, let's get into our electrochemical cell lesson. If you wish to use this lesson in your chemistry classroom, just click on the Astrid's Science resources in the description below. Most of my resources include teacher keys. Handy. This very simple microbattery setup currently involves a copper-zinc cell. Now, my students is showing you how you can change this from a copper-zinc cell, or should I say zinc-copper, to a magnesium-copper cell. She's hooking up the metal electrode to a magnesium strip after adding some magnesium electrolyte solution. And she's moving, hopefully with tweezers indeed, her salt bridge into the adjacent well. And we're getting more of a voltage with this magnesium-copper cell compared to the zinc-copper cell. Let's scroll through this document to see what's out there. As you saw in the quick student video, they are setting up a magnesium-copper voltaic cell, and next they compare that to a zinc-copper voltaic cell. Notice that there are some components highlighted in yellow. Besides regular chemistry, I also teach AP chemistry, and so I'm actually using this same lab with enhanced components in both the regular and the AP chemistry classes. I'm highlighting the single replacement type redox reactions here, using tables either from our New York State chemistry reference tables or from the AP chemistry textbook that I use. One of my students actually highlighted this particular video, removing rust with electrolysis, and he had tried pretty much this very method shown in this YouTube video. Here are some Google Photos videos that he shared with me to highlight his own experience from his own backyard, doing this as safe as possible. As you can see here, he was removing rust from an actual metallic object. What might that object be? What's an electrochemical cell lab without showing an actual Hoffman apparatus setup? It obviously requires a battery to decompose water with the resulting release of hydrogen and oxygen according to the 2-to-1 ratio. I have students fill out the diagram related to the Hoffman apparatus as I'm demonstrating it to them in my classroom. Another thing we don't want to forget either is that in order to be able to do these lithium and potassium demonstrations, it requires electrolysis to actually obtain these metals with their electrons still attached. Therefore, the last part in my electrochemical cell lab asked the student the following bonus question, required for AP chemistry. How is this electrolytic cell actually set up so that we can retrieve that pure sodium? In conclusion, as we are thinking about teaching various concepts in chemistry, it's always key to have that anchor phenomenon. This one centered around battery explosions. How can we do this safely? Bedankt voor het kijken. Thank you for watching. Tot ziens. See you in the next video.